Okay, students, hi there. This is Mr. Lewitt, and I'm doing my last video for the semester, my last video for this course, and my last video for the semester. Okay, so yeah, this is my Christmas wallpaper for one of my laptops. So happy holidays, happy Hanukkah, Merry Christmas, Happy Winter Solstice, whatever you celebrate during this time of year. Um, okay, so let's go over your probability quiz. I would like to go over the probability quiz and maybe, two or three, maybe four problems from your probability test. But I'm not going to go over the entire test. However, I will go over the entire quiz, and hopefully, this will help prepare you for your quiz and your test. Okay. So here's Mathematica, and as you all know by now, I use excuse me, I use Mathematica software quite a lot. I think it's a very good learning tool, and I think it's a very good teaching tool. And it is actually used by professionals. I mean, I know for a fact that there are professional data scientists that actually use Wolfram Mathematica. So it's not just used by college and university math teachers, it's really used in the industry. Now, of course, there are many different types of data scientists. Some of them use Mathematica, some of them use something else. some of them use the R program, some of them use SAS, some use MATLAB, some use Python, some use Java. Um, you know, there are many choices. There are many choices. There's a lot of different software applications and programming languages that are out there, but Mathematica is one of them, and it's very good. It is very good at what it does. Okay? Okay, so let's start with question number one of your probability quiz. A card is drawn. Let me see if I can make this just a little bigger so it's easier for all of us to see. There we go. That's nice and big. Do I want to make that bigger? That's a little too big. Okay. A card is drawn from a well-shuffled deck of 52 cards. Find the probability that the card is a black card or a 5. So you have to think about this carefully. So I know that we have the total cards is equal to 52. Okay. And the black cards, that's equal to half times 52, which is 26. Okay. So how many fives do we have? 5 cards. We have 4. Now, why is that? Well, because we have, the 5 of hearts, 5 of diamonds, 5 of clubs, and 5 of spades. And actually, I stand corrected. Let me enter 2 here instead of 4, because the 5 of hearts and the 5 of diamonds are red. The 5 of clubs and the 5 of spades are black. So we have two, two 5 cards that are black. Okay? So you see the word or here, or means addition. And so you're tempted to say, okay, so it's going to be 26 out of 52 plus 2 out of 52. And you think that's going to be the answer. Actually, that's not the answer. That's not the answer. Okay? This will be wrong. Okay, so why is it telling me it's right? Okay, I thought it was going to be wrong. So Um, oh, I see, because it's an or. It's an or. Okay, it's an or. So yeah, it is just, okay. It is just simple addition. And so yeah, that is going to be the answer. So, one second. Yeah, because it is simple addition. This is or. So what is the probability? Find the probability that the card is a black card or a five. Or a five. Okay, and I see what's happening here. If you, okay, now I understand what's happening here. So if I had put a four, if I had put a four here, yeah, that would be a problem, right? Because that would be 15 over 26, so that would be, you know, black cards divided by total cards plus 5 black cards divided by total cards, and that's going to be 15 over 26. That would be incorrect. That would be incorrect. However, this is 2. This is 2 because the 5 of clubs and the 5 of spades are already being counted in the set of all black cards. So once again, let me say that over again so that you guys get it. These cards right over here, the 5 of clubs and the 5 of spades, these these two cards are already included in the set of all black cards. These two are not. The 5 of hearts and the 5 of diamonds, these are red. And so they are, because they are red cards, they are not being counted in the set of all black cards. So that's why, actually, I should really say 5 red cards. Okay, so now I would have the right answer, which is 7 over 13. And indeed, we see that the answer is 7 over 13. Your input is correct. Okay, so yeah. Okay, I hope I did an okay job of explaining that. That was a little confusing, but I think you guys get it. Okay, I hope you get it. Okay, let's move on to the next problem. Over here, I'm going to erase my variables. Okay, so uh, let's say clear or let's say remove global. Okay, that just removes the variables. So now if I type black cards, you know, up here we can see that black cards is 26. Black cards is it's an expression. It's an expression that represents the number 26. 1/2 times 52 is 26. However, here I removed all of my user-defined values, my user-defined expressions. So now if I type black cards, this symbolic form, black cards, is simply returned to me unevaluated because it doesn't represent a number anymore. It doesn't represent a number or any type of expression. Okay? So let's go on with number 2. Let's move on to number 2. A standard 52 card deck has 4 13 card suits: 13 diamonds, 13 hearts, 13 clubs, and 13 spades. The diamonds and hearts are red, and the clubs and spades are black. So we talked about this in the previous problem. Each 13 card suit contains cards numbered from 2 to 10, a jack, a queen, a king, and an ace. The jack, queen, and king are classified as face cards. An experiment consists of drawing one card from the standard deck. Find the probability of drawing a black 5 of hearts. Okay, so that's not even possible because the 5 of hearts is a red card. It's not a black card. And because it's not even possible, the probability has to be 0. 0 divided by 52, which is simply 0. Okay, and let's see if that's correct. Your input is correct, score 100%. Okay, so that's pretty easy. We didn't have to do much math with that problem. Okay, let's go over problem number 3. In a family with 7 children, excluding multiple births, which means, twins, triplets, quadruplets, etc., what is the probability of having 2 boys and 5 girls? Assume that a girl is as likely as a boy at each birth. Now this is where we really need Mathematica. Okay, for this problem, Mathematica is fantastic. So we have 7 children. Okay, so I'm going to define a gender variable, and I'm going to call it boy, girl. Okay. So now, all possibilities. I'm going to use the tuples command, gender, and then I'm going to enter 7 inside of a list. Now let's see what that looks like. All possibilities. Let's table form it so it looks pretty. It's easier to read the output if I use the table form command or function. So these are all the different possibilities. Okay, you could have 7 boys, you could have 6 boys and then a girl, you could have 5 boys, a girl, a boy, etc., etc. These are all the different possibilities. And Mathematica does a great job of enumerating all of these different possibilities. Okay, in case you're wondering, the word I just used is hold on, let me see if I can. This is a difficult virtual writing tool, so it's not easy to use. So enumeration. The verb is enumerate. To enumerate something means to list all the different possibilities, to make out a list. So Mathematica is very good at enumerating the different combinations of the genders with, let's say, 7 children. Okay? So I have this stored in a variable called all possibilities, right? Okay, so the first thing I need to do is what's my denominator? The denominator is equal to the length of all possibilities. It's 128. So you have 128 different possibilities. Okay? Oh, just ignore that. That's my dog. We'll just ignore that. Okay, hold on one second. Chachki, please stop. Okay, so remember, guys, when you're figuring out a probability, stop. When you're figuring out a probability, okay, you have a numerator and you also have a denominator. So for this problem, my denominator is going to be 128 because we have 128 different possibilities. Okay, now what is the numerator? What is the numerator? So that we're going to have to figure out, right? Okay, so to find the numerator, let's look at the original problem. What is the probability of having 2 boys and 5 girls? Okay, so we're going to use the count function to help. How do you use count? Let's say I have a list of names. So Douglas, Susan, oops, wait a minute, I need quotation marks here. Douglas, Susan, Jack, Julian, Lee, and Sally. Okay, so I have a list of names, and let's say I have 2 Sallys in my list. Okay, oops. And I want to know how many times does Sally appear in my list. It appears twice because there are 2 Sallys in my list. So I can use the count function to help with this problem. So the numerator, well, let's first things first, before we even do that. Cases, all possibilities, and my variable is going to be, I'm going to call it sublist. My variable is going to be called sublist. And, or you can call it really whatever you want to call it. I like to call it sublist. You can call it XYZ. You know, you could call it ABC, but I like to call it sublist because that's really what we're dealing with. The count sublist boy is going to be equal to 2. And this symbol, the double ampersand, means and. Count sublist girl is, of course, going to be equal to 5. Okay, so now we see all of these different possibilities. And actually, if you have 7 children and 2 of them are boys, 5 of them have to be girls, which means if you want to, you could just eliminate this and you'll get the same answer. Okay, because that's kind of redundant. You really don't need to test for 5 girls because if there are 7 children and 2 of them are boys, you know the other 5 have to be girls. So then, you know, we're going to get the exact same answer as before. Now, how long is this list? The list is 21. So we're going to save this value and call it our numerator. This is going to be the numerator, okay? So the numerator is 21 and the denominator is 128. So numerator divided by the denominator is simply 21 over 128. So that's the answer, 21 divided by 128. Your input is correct, score 100%, okay? So that problem's maybe a little complicated, but I don't think it's that bad. It's really not that bad, okay? Let's move on to the next problem. An experiment consists of dealing 5 cards from a standard 52 card deck. What is the probability of being dealt exactly 2 face cards? So here, again, you know, we have to use some thinking. What are face cards? Face cards, okay, 1 second. So if you have a deck of cards, you have 52 cards in a deck. So face cards are jacks, queens, and kings. Those are the face cards in a deck of 52 cards. So you have, let me write this out. You have jacks, you have queens, excuse me, you have queens, and then you have kings, right? I'm just going to write this down. And then you have kings. Okay. So remember that in each, what's the word I'm looking for? I'm not sure if the right word is suit, but you have 4 different jacks because you have, you know, hearts, diamonds, clubs, and spades. You have 4 different queens, and then you have 4 different kings. You know, the king of spades, the king of clubs, the king of hearts, the king of diamonds, and the same for jacks and queens. Okay? So that means, you know, 4 times 3, or 4 plus 4 plus 4, that's 12. Okay? So how many face cards do we have? Face cards, we have, oops, sorry about that. Face cards, we have 12. Because there are 4 jacks, 4 queens, and 4 kings, and those are the face cards. Okay? So we need to figure out all the different combinations, and for that we're going to use the binomial command. We're going to use the binomial command to figure that out. So how am I going to do this? Well, we're being dealt 5 cards. So in the denominator, okay, clear numerator, denominator, clear numerator, denominator. So the denominator, which is, in my opinion, usually easier to figure out than the numerator, is simply binomial 52, 5. Because we have a deck with 52 cards and we're being dealt 5. So how many different combinations are there? It's quite a few. 2,598,960 different combinations, and that's quite a lot, right? So what is my numerator? My numerator is going to be binomial. I have 12 face cards, and I'm being dealt 2 times binomial. Now let me think for a moment about this. If I'm being dealt 2 cards, that means I have 2 cards less in my deck, which means now I have 50 cards, and I'm going to select 3. One moment. So I have 12 face cards. I'm selecting 2 of them. Oh, 1 second here, but there's something I'm missing. Okay. If you have exactly 2 face cards, that means the other 3 cards cannot be face cards, which means this would have to actually be 52 minus 12, which is really 40. So 52 minus 12 is 40, or we could simply write, stop, I'm talking to my dog, guys. So 52 minus the number of face cards, which is 12. So 52 minus 12 is 40. That's going to be 652,080. Okay, so then my probability is going to be numerator divided by denominator, and that's going to be 209 divided by 833. 209 divided by 833. Let's see if that's the right answer. Ooh, your input is incorrect, score 0%. That's not good. So what did I get wrong here? Okay, so 12 face cards, because 4 plus 4 is 8, and 8 plus 4 is 12, and I'm selecting 2 of them. Okay, one moment. Let me try to figure this out. Hold on a second. Let me pause this. Okay, so I see exactly what's going on here. So this actually is the right answer. Okay, this actually is the right answer. So I just wasn't reading the directions that well. The probability of being dealt 2 face cards is 209 divided by 833. However, I have to round to 6 decimal places as needed. I have to round to 6 decimal places as needed. So that's why Pearson is not accepting that answer. Okay. So yeah, I was wondering, like, I'm pretty sure that is the right answer, but Pearson wants a decimal. Okay, not a problem. So number form, numerator divided by denominator, infinity, and then 6. We want 6 decimal places is needed. Infinity here is a little hard to explain. Infinity simply means that I'm not limiting the number of significant digits in my decimal approximation. I'm using all the digits in my decimal approximation. Okay, or if I want to, I could limit that. I could say, well, I just want one significant digit in my decimal approximation. Okay. Oh, I forgot. Hold on. Sorry about that. I just want, here we go. I want one digit, one significant digit in my decimal approximation. Or let's say, for example, I could say two digits and two significant digits in my decimal approximation. Okay, but actually I want all of them. I want all of them. So if you want all, if you're not going to limit the number of significant digits, then the safe thing to do is to simply enter the option infinity, which simply means give me as many significant digits as possible. Okay, so here we go. Ugh, hold on. So the answer is 0.250900. That should be correct. Yeah, your input is correct. Score, yay, 100%. Okay? Excuse me. Okay, so test the pair of events B and E for independence based on the following table. Okay, so let's see. Let me make this a little bit smaller. Okay, so B and E. So the probability of B is equal to 0.30. Okay, and the probability of E is equal to, as we can see, 0.60. 0.60. Now, what's the probability of B and E together? It's this value right here, 0.18. Probability of B times the probability of E, is that equal to 0.18? It is, which means that the events are independent. If this was some other value, if it was not equal to 0.18, right, then you would say that B and E are dependent. It should be correct, so the answer is 100%. Okay. Let's go on to number 6. So similar to the last problem, we have to test for independence, the independence of events. Test the pair of events C and E for independence based on the following table. Are C and D independent or dependent, and why? Select the correct answer below and fill in the answer boxes to complete your choice. Okay, same as before. Okay, we're looking for C and E. So prob C, the probability of C is equal to 0.40, 0.40, and the probability of E, the probability of E is also 0. Let me make sure this is okay. Yeah, it's also 0.40. And what is the probability of C and E together? Right over here, right? So we can see the probability of E and C happening together is 0.11. 0.11. Okay, so what is the product of prob C and prob E? Well, let's see. I know 4 times 4 is going to be 16. And that's going to be 0.16, right? I think so. 0.16. Is 0.16 the same as 0.11? It is not. Okay, it is not. We know that 0.11 is not equal to 0.16. Okay, therefore we can see that they are not independent. The events are actually dependent. Okay, the events are dependent. So let's see. Option D or choice D. C and E are dependent because the probability of C and E happening together does not equal the probability of C times the probability of E. The probability of C and E happening together is, let's see, we're 0.11, and the probability of C times the probability of E is equal to 0.16. It should be correct. Your input is correct, score 100%. Okay. Okay, I'm going to finish the quiz, guys. I wanted to do a couple of problems in your probability test. That's going to have to wait until a little later, or well, a little later, or maybe tomorrow, because I am getting a little tired here, and I have to take care of my dog soon. So I'm going to finish the quiz, upload this to YouTube, and then I will email you guys the URL so you can watch the video. And the test, let's go over some, not all. Some of the problems in the test, we can go over that in a separate video, either later today or maybe tomorrow, and then I will email that to you as well. Okay. Problem number 7. Okay, similar to problems 5 and 6, right? Test the pair of events E and D for independence based upon the following table. Events A, B, and C are mutually exclusive. Events D and E are mutually exclusive, which means they cannot happen together. Okay, so let me see here. The total probability, okay, so the probability for C, is equal to 0.30, and the probability for E, the total probability for E is equal to 0.90. Probability of C times the probability of E, that's equal to 0.27, but the problem is if, oh wait, I'm sorry, we're doing the probability of D. Sorry, I made a little mistake here. Probability of D, the probability of D is 0.110. 0.110. Sorry about that. And the probability of E is 0.90. So the probability of D is 0.10 and the probability of E is 0.90. So then the probability of D times the probability of E is equal to 0.09. However, the probability of D and E happening together is equal to 0. And why do I know that it's equal to 0? Because it says here in the problem, in the description of the problem, that events D and E are mutually exclusive, therefore they cannot happen together at the same time. So the probability of D and E has to be equal to 0. Well, is 0 the same thing as 0.09? No, it's not. So we would say no, they are not independent. Let me see. Option B, no, they are not independent because the probability of E and D is not equal to the probability of E times the probability of D. The probability of E and D is equal to 0, and the probability of E times the probability of D is equal to 0.09. Your input is correct, score 100%. Okay. Okay, so what is going on here? Why is this not, oh, here we go. Okay, that was kind of slow. I'm not sure if that's because of Pearson's servers or if that's because of my internet connection or Wi-Fi connection. Okay, so for problem number 8, the question is, hold on guys, let me take a drink of water here because I'm just talking nonstop, which is not the greatest thing for my voice. All right. A single card is drawn from a standard 52 card deck. Let D be the event that the card drawn is a black card. And let F be the event that the card drawn is a queen. Find the indicated probability, the probability of D and not F. This is the probability of D and not F. All right? So D, excuse me, D is the event that the card drawn is a black card. F is the event that the card drawn is a queen. F prime means the probability, well, I should say the event. F prime is the event the event that the card is not a queen. All right. F prime is the event that the card is not a queen. Okay, so let's think about this. How many black cards do we have? How many black cards do we have? Black cards is 26. Okay. And what about the probability? How many cards are not queens? Not queens would be 52 minus 4, which is 48. And then we have the total number of cards, which is equal to 52. The total number of cards, which is equal to 52. So to solve this problem, basically you're going to take this probability here, the probability of a black card, of drawing a black card, plus the probability of drawing a card that is not a queen, minus the product of the two probabilities. So the probability is going to be black cards divided by total cards. Yeah, total cards plus not queens divided by total cards minus the product of the two. So we're going to have black cards, and I'm going to write it like this. Black cards times not queens divided by total cards times total cards, which is really the same thing as total cards squared, divided by total cards squared, and that's going to be 25 over 26. Type an integer or a simplified fraction. 25 divided by 26. Okay, what is the problem here? Why am I getting an incorrect answer? Oh, because I think I'm using, okay, sorry. I'm using OR logic here, and I should be using AND logic. I should really be using AND logic. So this is OR logic. This is AND logic. This is AND logic. So this means OR, and this means AND. So I believe actually the answer is simply going to be this part right over here. Six out of 13. Yeah, your input is correct. Score 100%. So if the problem was written like this, the probability of D or F prime, then the answer would be 25 over 26. But this is not what the problem is looking for. The problem is looking for the probability of D and not F, or D and F prime. So the way to figure that out would be eliminate this part, these two parts over here, and you're just going to have, black cards times not queens divided by total cards squared. Okay, so once again, guys, it's going to be black cards times not queens divided by total cards squared, or you could expand it. You could write it this way: total cards times total cards. Either way, you're going to get the right answer, and that answer is 6 over 13. 6 over 13, okay? Number 9. A single card is drawn from a standard 52 card deck. Let D be the event that the card drawn is a black card. And let F be the event that the card drawn is a 4 card. Find the indicated probability. So this time we're using OR logic. The probability of D or F prime. This is actually just like the last problem. In fact, I believe because we have 4 4s, you know what? Let me just, yeah, I think this is exactly what we have over here, 25 over 26. So let me see if that's going to work. I'm pretty sure that's the right answer. Your input is correct. Score 100%. Yeah. So there wasn't really much to do there. Okay. And because it's basically like the last problem, except this time instead of AND logic, I'm using OR logic. Okay. So remember, in probability, this means OR. This means OR. Okay. Whereas, sorry, this symbol here means and they actually do, that really does make a difference. It really does change the problem. So with OR usually means you're adding probabilities, and with AND you are multiplying probabilities. Okay, that's really the difference. Generally, that's the difference. Okay. Yeah, so that looks good. Okay, so find the probability of event W given event C by referring to the tree diagram and using Bayes' formula. Okay, the probability of W given C. Okay, so we're going to use Bayes' formula. Here, hold on one second. Let me... Okay, so that's the probability of W given C. Okay, so then we're going to have, if you look at the tree diagram, that's going to be 0.6 times 0.3. So that's this branch right over here. Okay, divided by, and then we have to add up all the C branches, okay? So that's going to be 0.6 multiplied by 0.3 plus 0.2 times 0.7 plus, so that's, that's this branch right over here. So we want the probability of W given C. Okay, it says here, find the probability of W given C by referring to the tree diagram. So what is the probability of event W happening given that event C has already happened? Okay. And then there's this branch over here, right, which is 0.2 multiplied by 0.6. And that's going to equal the answer. That's going to equal the answer, okay? So what is that going to be? 0, well, okay, 0.6 times 0.3. Control divide, but it's not quite what I want here. Highlight this whole thing, control divide by 0.6 times 0.3. Actually, I don't need parentheses here. Okay, 1 second. 0.6 plus 0.6 times 0.3 plus 0.2 times 0.7 plus 0.2 times 0.6. Okay, round to 3 decimals is needed. Round to 3 decimals is needed, so that's going to be, 1 second, hold on a second. Okay, 0.409. 0.409. Your input is correct, score 100%. Okay. So now, let me submit my quiz. Okay, terrific. Okay, so I expect everyone to get a really good score on this quiz. And if you didn't, that means you didn't watch my video. And you really are supposed to watch all of the videos that I send you. Unfortunately, this semester, I have not made I did not make as many videos for this particular class as I wanted to. This was a very, very busy semester for me. A lot of family stuff was going on, and I've got 2 other classes to teach. So, unfortunately, for this class, I feel like I could have made a few more video lectures for you. I feel like I did not make as many as I wanted to. I made some. I could have made more. So, but hopefully, this will help you with your quiz. And if you fail the quiz, that tells me that you're not watching my videos like you're supposed to, and you're not using Mathematica like you're supposed to. Okay, so that's about it for now. Now the test, I will go over some of the questions in the test in a separate video. I don't want to do that now, guys, because I have some back issues, and so sitting for hours and hours and hours in front of a computer without a break is really bad for my back. So, and I also need to take care of my dog and do some other things, okay? So what I'm going to do, I will do some of the test, not the entire test. I will do some of the test questions. Excuse me. I will do some of the test questions in a separate video. And I will try to get that done, no later than Sunday. Today is Saturday, December the 12th. I will try to get that done no later than Sunday, December 13th. And of course, I will upload these video lectures to YouTube, and I will send you the links so that you can watch these videos. And hopefully they will help you to do extremely well and pass your quiz and test with amazing scores. Like I said, if you don't do really, really well on the probability quiz and test, that just tells me you're not watching my videos. And okay, why aren't you watching my videos? That's your responsibility, right? Okay, all right, guys. I think that's going to be it for today, or at least enough. Maybe later I'll do that other video for you guys, probably tomorrow. Okay, take care, get your quiz done, and watch the video, get the quiz done, and I'm sure everything will work out really well. Okay, happy holidays. Take care. Bye bye.